Hello, I'm Zach from Metru. This is Metru's integration sphere. This is our 2-meter sphere, so it has a diameter of 2 meters. Typically, spheres are used to gain the total radiant power measurements, and then sometimes the color measurements depending on if you were using a spectral radiometer or a photometer. The size of the sphere depends on the size of the luminaire. So the light source. So the light source should have a total surface area of 2% of the total inside surface area of the sphere, and its longest dimension should only be 2/3 of the diameter of the sphere. So in our case, we have a pretty small lamp in there, so the 2-meter sphere is definitely more than enough. So our sphere is composed of the sphere itself, and then we have the frame in which we have, it opens and closes, which I'll show you in a minute. We have a storage area down here on the bottom. Inside we have 2 mounting systems. We can mount lights in the 4-pot, which is shown here, or we can open this port over here and mount directional lights in 2-pi orientation. LM789 recommends 4-pi, but sometimes if it's too big, then you have to put it in the 2-pi. And then we also have a cabinet over here with all of our measurement tools. So we have a power meter, a DC power supply, spectral radiometer, and the AC power supply. Across the side down here, we have all the ports for our wiring, which you have to change depending on if you're using DC or AC. And the inside of our sphere is coated in barium sulfate, which has approximately 97% reflective. It's diffusively reflective, which it has to be. The goal of the integration sphere is to diffuse the light such that across the surface area of the inside of the sphere, no matter where you take a measurement, it will have the same radiant power distribution. So you could theoretically take a measurement anywhere. However, you'll notice that inside the sphere we have a couple baffles. So the baffle is to prevent direct light from the light from hitting the spectral radiometer, which will offset a measurement, and it will also prevent any first bounces. Over here you will see a baffle, and behind it is our auxiliary lamp. The auxiliary lamp is used to calibrate the self-absorbance of the lamp itself, so it emits light in a broadband spectrum. Other than that, LM789 says that you should have a the reflectance should be between 95% and 98%. The reason for that is the higher your reflectance, the better your signal is, and the less error you will gain from spatial non-uniformities of the coating itself and the lamp. But the more reflective it is, the more sensitive it is to self-absorbance. Other than that, our system here is a complete system. So we have the software and then all of the measurement devices you would need to do LM789 testing. Next part of this video, we'll go over the software that we have, and that's it for now. Thank you.
This is the second part of Metru's integrating sphere video. In this part, I want to go over our software. So just to briefly go over it again, this is I am currently using the 2-meter sphere. All of our integrating sphere systems are a complete system, so you don't need any other hardware or software to do LM789 testing. And we do provide different size spheres. So I went over briefly before what you need, like what are the requirements for your size, and I'll do that again briefly. So your luminaire surface area has to be less than 2% of the total inside surface area of the sphere. And the longest dimension, so typically the length of the luminaire, has to be 2/3 or under the diameter of the sphere. Here at Metru, we have a couple different sizes. We sell a 0.3 meter, a 0.5 meter, a 1 meter, a 1.5 meter, a 2 meter, and a 3 meter sphere. In the 0.3 and the 0.5 meter spheres, you don't need an AC power supply or power meter to come with it, and that is because those spheres are designed for LED chip testing. So LED chips typically don't include their own drivers, they're DC powered, so you just need the DC power supply, and then with those systems come with what are LPS 300, which is a programmable DC power supply. So it integrated in that LPS 300 is a power meter. I also wanted to mention that all of our current models come with a thermometer inside the sphere, and that as you take measurements, it will take the measurement inside the sphere, which LM79 says that when doing testing, you have to be within 1 degree of 25 degrees Celsius. So in this video, I'm using a slightly older sphere, and I don't have the thermometer inside, so I won't be able to show you that part. I have to manually input, but in the future, all temperature measurements are taken automatically along with the radiant power measurements. So the first thing I want to do is, let me open my software. I'm going to run through like a typical procedure. So typically the first thing you want to do is calibrate. Mine is already calibrated, but I'm going to show you the calibration screen. So if I go to calibration, spectrum calibration, here's what it looks like. I have a lamp type, which is a source lamp or a lamp file. So a source lamp is you just input all of these manually. A lamp file is if I already have a file for my standard lamp, then I can select it here, and it will automatically put in the parameters for that lamp. We almost always want to do flux calibrations. And then over here we can hit start, and it will take its time, and it will end automatically. The dark here is done automatically in the start, but you can also do it manually, and that is just taking the dark current. So because this is an array spectrometer, spectral radiometer, it will always register some current. So light will induce a current on the spectral radiometer when it hits the detector, and to get an accurate measurement, we need to subtract the current that is already present, and that is what we call the dark current. So I'm going to leave this screen. So actually, before calibration, we would have to turn on our luminaire or our standard lamp, and you would do that by going to Analysis and DS300, DS1200, depending on what one you're using. Here's the screen. You can select the one you're using, and you will always set it to current because standard lamps are calibrated based on their current. So the current is always held steady. So you would select this, set the current to what it needs to be, hit set, and then you want to read it to make sure it's what you want it to be, and then you can do your calibration. Seeing how we've already done that, we're not going to do this. I have a LED in there so that the DS would destroy the LED, so because there's a driver. So I'm going to use my AS power, which is AC. It's called AS because our AC power supply, this model name is AS. And I do have the AS 1000, and it is, I don't think it's in COM5. Oh no, I think it is in COM5. Okay, so we can hit remote. It's already on. Oh, it's not COM5. Maybe COM4. Okay, so it's COM4. I can also check that in my device manager. So it's there. I'm going to set it to, this is typical parameters for US power. So my frequency range is 45 to 60. voltage range is 15 to 220, and the output voltage is 120. So I'm going to hit set OK, and then output. And my lamp has turned on. So up here it will tell you that my lamp is currently at 120.1 volts. The current is 0.088 amps. Power factor is 0.988. The power is 10.4 watts, and then the frequency is 60 hertz. So that's good. I'm going to leave the screen. And now my lamp is on. So before you actually take a measurement, for LM79 testing, you would do self-absorption calculations. So this is going to give you a self-absorption factor to correct your measurements. So when you put a lamp inside the integration sphere, it's going to absorb some of its own light. So to counteract that, in our total radiant power measurement, we use the auxiliary lamp, which emits a broadband spectrum over the spectrum that our spectral radiometer can measure at, which in this case is the visible range. So in order for it to do that, we install our standard lamp. We turn it off and make sure that it has cooled down so that there's no radiant power coming out of it. And then we would test it, and it will give us a coefficient here. Then we put in our test lamp, keep it off, and test again, and that will give us another coefficient, and then our software will calculate the total self-absorption factor, and we can save it and then load it in here. And I'm not going to do that right now because I have my lamp on and I have not installed the standard lamp. But in a typical measurement, that's what you would do. And exit. Let's see. So that's about it for the calibration. And under analysis, we also have a VS time curve test. This just gives you whatever you like over time. So current, voltage, power, flux, color temperature, and then color coordinates. And if I were to test it, which I'm not going to because it takes a little while, here's got from 0 to 1 hour. It will, although I can show you a measurement, it will measure the flux of my lamp as it changes over time. So it should decrease a little bit because I just turned it on. So I might say if it stays straight, then it's stabilized pretty quickly, which looks like it's staying pretty flat. We can look at the actual numbers as well. So it is decreasing a little bit, but not too much. Oh, and then it increased. So now it's staying flat. And that's fine. I guess my luminaire is already stabilized for the most part. But, so I'm going to stop it. Stop test. Exit. Okay, so now I'm going to go to the operate, system startup, setup. So here's my integration upper limit. Photometry type, we're almost always going to use flux, but you also have the option to use illuminance, intensity, and luminance. Sensitivity can be high or low. Typically we use high, but if you have a very intense lamp in there, you can potentially oversaturate the spectral radiometer. So then you would turn this from high to low. Test mode will be fast or precise. Precise just means that you are going to use, we have some broadband or broad pass filters in there, and you can use those to, so the broad pass filter is just going to eliminate certain frequencies. So you can use that to eliminate stray light. So it'll give you a slightly more accurate measurement, but it will also take quite a bit more time. And then you can also choose to use just the weak or just the strong filters. Precise will use all of them, and fast I can use one or the other. For this test, I'm not going to use either. Then down here is wavelength range. For us is the visible, so that's correct. And then you can also set a trigger mode so that it takes measurements at precise locations. Time test is useful because for LM79 testing, you're supposed to take a test every 15 minutes. So I can come here, I can set it here, so every 15 minutes, and say use time test. And then when I hit take a single test, it will take a single test at each of these intervals. Spectral radiometer, this is just the model that I'm using, the port that it's at, and date format. Power meter. So this is going to use a power meter to get all of my electrical parameters. So power, current, voltage, power factor, and then what port it's at. And then down here, I can stabilize before test. So I can leave it alone, and then it will take the test when it judges it to be stabilized or at a certain time. So I'm going to hit OK. Now I am ready to take a test. If I hit operate, single test. So here is the spectrum for the LED that I have in there. Down here I can see the flux, the power, the efficiency, the color coordinates, color temperature, IP, which is 73%, the dominant wavelength, color purity, the peak wavelength, the full width half max, the red ratio, the general CRI number, and the SDCM, that is the standard deviation color matching, also known as the McAdam ellipse, which is their ellipses in CIE color mapping 1931, where the human eye can't distinguish between colors. And that's shown here. It shows the point and if it's within a certain one or not. This is just one of those ellipses. Here I have the 1931 CIE, 1976 CIE, and the spectrum. I can change all of these, what these columns will show me if I go to view information. Oh, I'm sorry, not information. Information just shows, this is stuff that I can input and it will print out with the report. So the sample number that I'm using, the sample, which none of this is true, the standard lamp that I used to calibrate, the temperature that's at, which let me check real quick. I have 55.6, so I actually am within LM79 LM79's constraints, and the humidity, which I have here, which is currently 43%. This is the test, which is me, the date, which is today, and the time. And the remark, I can just hit demo. That's not how you spell demo. Sample number, 00, sample, demo. Manufacturer, demo. Alright, so I hit OK. Sorry, so if I go to option, here I can show what parameters I want. So here I have CIE 1931, 1976, SDCM, white, which is all down here. I have the report title, that's fine, company, address. I can go to parameters, so I can show the number, that's just 1, 2, 3, 4, voltage, current, power, CIE coordinates, here I'll check that too, dominant wavelength, peak wavelength, this is full width half max, red ratio, color purity, general CRI coordinate, CI coordinates 1 through R15. The one that most people care about is R9, which is the red color. IP, flux. Alright, level we can set. So you can set it so that if you need your your light source to be at a certain level, if I check this, it will say if it passes or fails that level, and I can set the levels elsewhere, and I can have as many levels as I wish. White is the white class. Information is if I want to show the information that I just set where I labeled everything as demo. Scotopic vision and SP, which is scotopic to photopic vision. And that's about it. So I'm going to hit OK. Oh, and then over here I just have a couple options. So this is the text color and the background color. I'm happy with white and black. I'll hit OK. So if I go to operate, level edit is where I can set my levels. So there's a couple predetermined, like just a couple sample ones that we set. Class 1, Class 2, Class 3. And over here we have what it has to pass under. So this is the power and then the luminance. I'm not going to worry about that today. So I also have the option to take a multiple test, which I can click here, or I can go to operate, multiple tests, and it will continuously take tests. So 1 and 2, and it'll just keep taking tests. So that's useful if I want to see the how the lamp is changing with time. I can also use what I showed you before. Let me stop this. I can also use what I showed you before on their level, which was the verse time curve test. And then I have the white level edits, and that is about it for test taking. I also have a few options for exporting. So I can export it to Excel. I can export it to Excel with the spectral data, or I can export to a PHS file, which is a file that Mitru typically uses. And then I can also print it as a, print. I can also print the report as to a PDF if I have Adobe Acrobat on my computer, which I do, or Microsoft XPS, which will be on any Microsoft computer. After I hit OK, it will print. Oh, it's asking me to save it. Documents, I'm going to put it desktop. Integration sphere demo report. Save. And it will print the one that I had highlighted, which in this case is the last one. So it's thinking about it. And this will just print a standard Mitru report. So it'll just have all of the data that I have measured. And then one final thing you can see on my side window over here, I have some more information. So the colorimetric quantities and the photometric parameters, electrical parameters, and the system. So these are just the settings that I set before. So under here we have red ratio, green ratio, blue ratio, which I only showed red ratio before over here. And then here's my report. And I can scroll down. Here's all of this information up top here. I previously set under the view information. The test conditions, I took fast tests. Here we can change actually what information it will show. But I have the test conditions on top. Spectrum, CIE 1931. Color quantities. Photometric and radiometric quantities, electrical parameters. This is never mind, I take it back. These are all 7 of the tests that I just took today during this demo, not just the one. And that is about it for this. I'm going to briefly go over the benefits of using an integration sphere. So when you use an integration sphere, one of the benefits is that you get fast measurements. So unlike the Ganyo, which takes about easily a couple hours at least, the sphere, as you just saw, took me 30 seconds if I already have it calibrated. I can just take a measurement. The integration spheres take a small amount of space. You can roll them in the corner, still take measurements. You don't need a big hallway to direct light across. You don't need a dark room. It's all contained in the sphere. Our spheres are complete systems, so you don't need anything else to do LM79 testing or to get any information other than spatial information. And then our integration sphere also comes with the spectral radiometer, which is recommended by LM79 as opposed to a photometer. This is because photometers have spectral mismatch errors associated with them and LEDs, and those can often be difficult to account for and calculate. So that's why you would want to use the spectral radiometer, as well as you get the spectral information. And that's it for our integration sphere video. I hope that this was helpful. If you have any questions, please feel free to contact us at sales@metru.com or at our phone number, which I will put in a citation below. And our website is www.metrue.com. And thank you for your time.